In today's lesson, we're going to find the order and the size of a complete multipartite. This is problem number 5 from this week's assignment. To start with, let's look at examples. Let's start with a bipartite. As you can see in this example, we've got a bipartite of 3, 2. So 3 elements in set A1 and 3 vertices in set A2. So we're going to take a look at how you find both the order and the size of a bipartite of these given set sizes, and then we'll expand it for all cases. So as we look at this, what we have learned is that to find the order, we just simply count the number of vertices. So we have 3 plus 2, we get our 5. To get our size, we count the paths. So I have noted them in color, so we just simply count the purple ones, the red ones, and the green ones. And so we end up with, just by counting, a process of getting the answer of 6. And then what we started looking at was how would we look at this if it were an infinite set. And after we looked at several sizes, we came up with different ways of seeing the patterns. And so on this particular problem, what we see is to find the order, we do indeed add the vertices. What we found with the size was when we multiply the elements of set 1, which is R1, plus the elements of R2, which is our set 2, we actually end up getting a binomial times a binomial. And when we multiplied them, we found out that we are including the intersets, which are not existent in a bipartite. So we end up having to subtract out the intersets, and we need to then eventually divide by 1/2 because we do not want the purple line counted twice. We don't want to count from left to right and right to left. So we end up finding that our size on a bipartite is R sub 1 times R sub 2. Okay, let's look at a tripartite. Here we have an example of a tripartite size 3, 2, 3 with all of the paths showing all of the possible scenarios. So in a tripartite, as we take a look at it, for the order, we do the same thing. We add the vertices, and we get a total of 8. And I counted the vertices and ended up with a total of 21. Well, as we take a look at the multiplication, to find the vertices for all cases of a tripartite, it's R1 plus R2 plus R3. To find the size, we're going to take the polynomial R1 plus R2 plus R3 times the polynomial R1 plus R2 plus R3. And when we multiply it out using our distributive property, noted here, then we start looking at it algebraically to see what we can do. What I have put in the boxes are showing those values that would be the intersets. That would be the ones that we connect within each set, and those are not allowed in a partite. So we want to go back, and we got rid of those. And as I take a look at adding like terms, and you can see how I've matched them up, so to end up with getting our size of a tripartite, it's 2 times the quantity, R1 times R2, plus R1 times R3, plus R2 times R3. So how can we expand this to a k-partite? As we look at a k-partite, what we want to know is what it is k sub R sub 1, comma R sub 2, dot, 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 up to size R sub k, with the k sets of vertices a sub 1, a sub 2, a sub k, where size is denoted by a sub I as being R sub I. To find the order, just as we did in the 2 examples, we simply add the number of vertices. So we're going to add R sub 1 plus R sub 2 plus R sub 3 all the way up to R sub k. And so if we want to write that into a correct summation statement, then we have the sum as I starts at 1 and goes to k of r sub I. Moving on, how do we then show finding the size? To find the size, we again are going to multiply. So as we multiply, we're going to take the quantity r sub 1 plus r sub 2 plus dot 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 up to r sub n, or excuse me, r sub k, and then we're going to multiply that times the quantity r sub 1 plus r sub 2 plus dot 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 r sub k. Now we have the same things happening here that we found happening on the bipartite and the tripartite. That being, first of all, again, we do not want those intrust sets to be included, and then we have to take care of the duplication. So we have to do the following things. We have to subtract out the intraset values. Intraset meaning when you have R1 and R1 together, R2 and R2 together, R3 and R3 together. And then we want to, again, add them up, but then we are going to have to multiply by 1/2 so that we do not end up with the duplication. In other words, we don't want to go to one ordered pair or from one set to the other and back again. We don't want to count that path twice. So, to eliminate the duplicating paths, we would multiply or divide by 1/2, multiply by 1/2 or divide by 2, whichever is your preference. And so we show it in our summation. So we have the size, to find the size of a k multipartite, it's 1/2 times the quantity, summation, where I equals 1 to k of r sub I, times another quantity, summation, where I equals 1 to k of r sub I, minus the summation, where I equals 1 of k of r sub I times r sub I, and close the main quantity. So what we're seeing here is this piece is going to subtract our intrust sets. This is going to, when we do the subtracting, I guess we are not doing the subtracting there. The 1/2 is then going to take care of the duplication. And that's how we find the order and the size of a k-partite.